Hi everyone, I'm Mukesh Mitrakumar. I work as a senior machine learning engineer at IQVIA, and I'm excited to present my talk on training a distributed named entity recognition model for drug, disease, and condition identification. The talk will be broken down into 4 components, starting from an introduction to named entity recognition. Then we go through BERT. There are a lot of approaches to named entity recognition, starting from classical machine learning approaches to deep learning approaches using LSTMs and CNNs. But I went with BERT because it has been the leading architecture in the industry for the last couple of years. Then we look at distributed training, and finally, how we can do distributed named entity recognition training. So, starting with named entity recognition. Named entity recognition is a part of information extraction where the goal is to locate and classify named entities. As per Wikipedia, a named entity is a real-world object. It can be abstract or have a physical existence, such as persons, locations, and organizations that can be denoted with a proper name. For example, if you take Mukesh Mitrakumar started working on NLP at IQVIA in 2020, here Mukesh is an instance of a person, IQVIA is an instance of organization, and 2020 is a date. Formally, we can define named entity recognition as given a sequence of tokens, a named entity recognition task is to output a list of tuples, each of which is a named entity. So how does named entity recognition work in healthcare? In healthcare, named entity recognition models are essential for identifying and extracting entities like diseases, tests, test results, and treatments from medical texts. Medical named entities are prevalent in biomedical text, and they play critical roles in boosting scientific discovery and facilitating information access. But a major challenge in disease named entity recognition is disease names are usually generated by combining Greek and Latin roots and affixes. For example, hemochromatosis. And more unknown names are difficult to identify from a morphology aspect. And many disease names are also frequently contain disease descriptive modifiers, if you take liver cancer, for example. And these modifiers may be related to human body parts or degree of disease, like recurrent cat eye syndrome. This may cause difficulties in identifying modifiers from other types of medical named entities like syndrome. Moreover, disease names may have multiple representation forms. For instance, hectical complaint and recurrent fever are the same disease but represented differently. Finally, there also exist a large amount of disease named abbreviations in medical texts. Some of them may not be standard, such as those user-defined abbreviations listed in appendix of a clinical trial text, and all these provide great challenges and opportunities. There are a large number of medical texts like PubMed, PMC, OA full text, and even Wikipedia, which is what BioBERT is trained on. We will look at what BioBERT is in the upcoming slides. You can also use any other type of medical data for named entity recognition, like electronic health records, to using social media like Twitter data to analyze user messages to detect and manage public health events. So let's look at BERT. BERT makes use of transformers, an attention mechanism that learns contextual relations between words or subwords in a text. In its vanilla form, transformers include 2 separate mechanisms, an encoder and a decoder mechanism. The encoder reads the text input and the decoder produces a prediction for the task. The input is a sequence of tokens which are embedded into vectors and then processed in the neural network And the output is a sequence of vectors, again, in which each vector corresponds to an input token with the same index. So if we dive a little bit deeper into BERT, the BERT uses two training strategies. First, the masked language model. Here, before feeding word sequences into BERT, 15% of the words in each sequence are replaced with a masked token. The model then attempts to predict the original value of the masked words based on the context provided by other non-masked words. In technical terms, the prediction of the output words require three things. First, you need a classification layer on top of the encoder output. Second, multiplying the output vectors by the embedding matrix, transforming them into a vocabulary dimension. And third, you need to calculate the probability of each word in the vocabulary with softmax. Second, next sentence prediction. In the BERT training process, the model receives pairs of sentences as inputs and learns to predict if the second sentence in the pair is the subsequent sentence in the original document. During training, 50% of the inputs are a pair in which the second sentence is the subsequent sentence in the original document, while the other 50%, a random sentence from the corpus, is chosen as the second sentence. The assumption is that the random sentence will be disconnected from the first sentence. So to help the model distinguish between the two sentences in training, the input is processed in the following way before entering the model. First, you create a CLS token. It's inserted at the beginning of the first sentence, and a SCP token is inserted at the end of each sentence. So a CLS and a SCP. So something like this. Second, sentence embedding indicating sentence A or sentence B is added to each token. Sentence embeddings are similar in concept to token embeddings with a vocabulary of 2. And third, positional embedding is added to each token to indicate its position in the sequence. The concept and implementation of positional embeddings are presented in the Transformer paper. I've added the link to the paper in the reference. Finally, to predict if the second sentence is indeed connected to the first sentence, you perform 3 steps again. First, the entire input sequence goes through the transformer model. Second, the output of the CLS token is transformed into a 2x1 shaped vector using a simple classification layer. And 3, you calculate the probability of each next sequence with a softmax. So when training the BERT model, the masked language model and the next sentence prediction are trained together with the goal of minimizing the combined loss function of the two strategies. So how do you use BERT for named entity recognition? There are multiple variations of BERT for named entity recognition, including BioBERT, clinical BERT, SPACY BioNER. Most of these are just variations of BERT trained on different datasets. For example, the clinical BERT uses text from all node types and discharge summary. So depending on your use case and data available to you, you can build a custom BERT or use a pre-trained one. In named entity recognition, BERT receives a text sequence and is required to mark the various types of entities, like person, organization, date, that appears in the text. So using a BERT, a named entity recognition model can be trained by feeding the output vector of each token into a classification layer that predicts the named entity recognition label. So for my use case, I use BioBERT. BioBERT is a model that is pre-trained on the biomedical datasets. In the pre-training, weights of the regular BERT model was taken and then pre-trained on the medical datasets like PubMed abstracts and PMC. So one of the challenges in creating production-ready named entity recognition is the limited number of entity types. And even if you have data, you would need to hire specialized annotators. So For the first version of my application, without hiring annotators to increase entity types, I used other biomedical domain-specific named entity recognition datasets, and the datasets are again linked in the reference as well. So let's look at what's distributed training. Distributed training distributes training workloads across multiple mini processors known as worker nodes. So these worker nodes work in parallel to speed up model training. And this parallelism can be achieved by data parallelism or model parallelism. So let's look at what's data parallelism and what's model parallelism. So in data parallelism, the data is divided into partitions where the number of partition is equal to the total number of available nodes. The model is copied in each of these worker nodes, and each worker operates on its own subset of data. And each node independently computes the errors between its predictions for its training samples and the labeled outputs. In turn, each node updates its models based on the errors and must communicate all of its changes to the other nodes to update their corresponding models. Whereas in model parallelism, it's also known as network parallelism, the model is segmented into different parts. Data parallelism, you segment the data. In model parallelism, you segment the models. And the model is segmented into different parts so that it can run concurrently in different nodes. And each one will run on the same data. So the scalability of this method depends on the degree of task parallelization of the algorithm, and it is more complex to implement than data parallelism. So when you have these two types, how do you pick which one to use for your use case? So if the deep learning model can fit into one node, go with data parallelism. And if the model is too large to run on one node, but the data set can fit in one node, then go with model parallelism. So distributed training for BERT itself. A major advantage of pre-trained models is their ability to adapt to specific tasks by using relatively small amounts of labeled data. But the base version of BERT has 110 million parameters. So pre-training is computationally intensive and takes days to train, even on the most powerful single node. And so that's the main reason why you need to use distributed training for BERT. So basically to speed up your iteration. And yeah. So how do you do distributed training? There are some popular platforms and libraries that allow you to do distributed training. And for my application, I went with Horowitz. So what is Horowitz? Horowitz is a framework open sourced by Uber for distributed deep learning. Horowitz's core principles are based on the MPI concepts like size, rank, local rank, all reduce, all gather, and broadcast. Here, MPI stands for the message passing interface, which is a standardized and portable message passing standard. Let's take a small example to explain the core concepts of Horowitz. So say we launched a training script on 4 servers, each having 4 GPUs. If we launched one copy of the script per GPU, then the size would be the number of processors, in our case 16. And the rank would be the unique process ID from 0 to 15. This is the size minus 1. And the local rank would be the unique process ID within the server, starting from 0 to 3, 0, 1, 2, 3 for the 4 servers. And all reduce. So all reduce is an algorithm for fast distributed training, and Horowitz uses all reduce rather than using a parameter server approach. The parameter server approach is what's used in TensorFlow's distributed training strategy. So Horowitz, in addition, also includes multiple optimization methods to make distributed training faster. So what exactly is the all reduce algorithm? So remember, if you are doing data parallelism, there are three major computation steps. One, you compute the gradient of the loss function using a mini batch on each GPU. Two, you compute the mean of the gradient by inter-GPU communication. And three, you update the model. So to compute the mean in the second step, you use a collective communication operation called all-reduce. Then you use all-gather. That's the operation which gathers data from all processes on every process. And finally, you use broadcast, which broadcasts data from one process identified by the root rank onto every other process. So we looked at named entity recognition, how it applies to healthcare, and then BERT, and how you can do distributed BERT training using Horowitz. So how do we put all this together? So I use a pre-trained BioBERT implementation from DMIS lab. This is open source code available. Again, links are in the reference. But to put all this together, the first thing I did was to convert the original BioBERT implementation to my use case. And below are the steps that I took to modify BioBERT. So the first thing that I did was the DMIS BioBERT is based on TensorFlow 1, but my business use case was to use TensorFlow 2. So the first thing that I did was to port the code from TensorFlow 1 to TensorFlow 2 and made sure it worked in the base use case. Second thing that I did was I added extra pre-processing steps so I could include more data sets to train my algorithm, because the original one in DMIS lab does not come with enough entities. So specifically, the major change was I had a lot of data in the BIOS schema. BIOS schema is a common tagging format for tagging sentence tokens. And I changed this to kernel format. So kernel format is a standard format. It's basically a space separated format. So while doing this, I ran into a few issues. So just a few things to keep an eye out for. One, we are doing token classification instead of sequence classification. So watch the labels you put into your algorithm. And two, different data sources may have different annotation systems. Sometimes it's easy to align those so you don't end up with separate pre-processing steps for each data source, and sometimes it's not. So just make sure you have test cases to verify these. And three, since named entity recognition use phrases rather than individual words, you need to use a specific format called IOP. And not all named entity recognition data sets come with this. And one option is to use spaces by-low tags from offsets, which will help you convert those formats into the format that you need. The second step that I did to add distributed training part to the BioBERT implementation. So I also added a hyperparameter tuning step to the code base using retune. So BioBERT can be tuned when we retrain the algorithm. And finally, how would Horowitz work for my data? So we split the data between the number of GPUs available. And from the coding side, you need to initialize the library, pin each GPU to a single process, and set up communication between the GPU workers. The training steps for each GPU is then divided by the number of GPUs available. And then what you do is you wrap the original optimizer by Horowitz distributed optimizer, which handles all the under the hood all-reduce calls. Using the distributed optimizer, Horowitz does synchronized parameter updates. And these steps are more detailed in Horowitz with TensorFlow. It's given in their documentation. And again, I have added the link in reference as well. So for my application, we were able to reduce the training hours from around 8 hours to around a couple of hours with 4 GPUs. This was acceptable from a runtime and cost perspective. So if you look at the GPU scaling efficiency, it's not really linear. And one of the major reasons for this is the inefficiencies in communication between the GPUs, since you're working with billions of floats over the network. So there were a lot of challenges in getting the first version up and running, but here are some general tips that you can keep an eye out for. So first one, make sure you set up a way to profile your code. Horowitz has something called timeline, and NVIDIA has NVProf to view any bottlenecks. So identify what your problem is before trying to actually solve it. Second, setting up communication between GPU workers. There are tons of resources on how to do this online, but not everything is going to work for your application. So make sure you take the time to find out the configuration that is the closest to your use case. Finally, there are some known communication bottlenecks in internode communication, since most of these libraries are pretty new. So check Horowitz's GitHub pages, GitHub issues page for any potential solutions. For most of the issues I had, I was able to find solutions in GitHub rather than Stack Overflow. So make sure you check there if you run into any issues. That's it. And if you have any questions, you can let me know in the chat, and you can also reach me in LinkedIn or Twitter. And here are the references. The code base is at Distributed NER. I will push the code soon after the talk. And these are the data sets and some for the links which can help you set things up in AWS and do distributed training. Finally, use BERT Explains. It's a pretty good article on Medium on how BERT works. I would highly recommend taking a look at that. And that's it, folks. Thank you.